Hey everybody. This lecture is really based on what we found last time. Last time we were looking at how we could look at this special case of constant acceleration and come up with some kinematic equations that allow us to do a lot of calculations relatively quickly. Everything that we did, not only in part A and in part B, was all in one dimension. But it turns out a lot of that stuff also applies in 3 dimensions. And so this is going to look at, so the title says it's 2D, but it's really 3D. It can look in all of those directions. But because this is an introductory course and we want to have everything on a piece of paper, then we would like to do it in 2D instead. But the rules are still exactly the same. Now, how do we know that the rules are going to work the way that we might anticipate? Well, it turns out if we were going to go to look at the case of motion in 2D or 3D, what we really have to do is look at the position vector in 3-dimensional space. And if we're keeping track of the variable x, we're keeping track of the variable y, we're keeping track of the variable z in each of their respective directions, we have kinematic equations that apply for all of those things, as long as we can resolve x position, y position, and z position, as long as we can resolve velocity components in the x and y and z directions, and we can resolve acceleration components in the x, y, and z directions, then really what is happening in each of these 3 component directions is what is shown here. xi plus vi in the x direction times time 1/2 ax in the t direction. This is everything that's happening in the x direction. Everything that's happening in the y direction is shown here. Everything that's happening in the z direction is shown here. And so you tell me what the initial velocity is in each of those directions, what the acceleration is in each of those directions. It has to be constant, but they don't have to be the same in every direction. It just has to be constant. That's totally fine. And you tell me where the thing started, and I will tell you at every instant of time where that thing is going to be. And because the velocity is the change in position with respect to time, we can take the derivatives of each of those things with respect to the x, y, and z directions, and we get these terms shown here. So yeah, we can have constant components ax, ay, and az. They don't have to be the same constant. They just have to be constant. And you tell me how time evolves, how fast it was going initially, and I'll tell you what it's going at some later time. If we were to take another derivative with respect to time, all that we would have left over is ax in the x direction, ay in the y direction, az in the z direction. That's the acceleration, the constant acceleration that doesn't depend on time. So we see that this is going to work by the definitions given to us initially in kinematics. But what if we wanted to rearrange terms and look at this differently instead? Well, we can take the xi, the yi, and the zi. Each of those has their respective x hat, y hat, and z hat with them. Well, why don't we just group all of those things together, those terms? We get xi in the x, yi in the y, zi in the z. This is just the initial position. That's all it is. And what if we were to group all of these second terms? Vi in the x direction times t, vi in the y direction times t, vi in the z direction times t. Each of those has their respective x, y, and z. Group all of those things together. Well, this is just the initial velocity times time, vectorially speaking. And what if we were to group these last terms, 1/2 ax t squared in the x, 1/2 ay t squared in the y, 1/2 az t squared in the z. Group all of those together. This is 1/2 times this acceleration vector t squared. So position is defined by the initial position plus the initial velocity vectorially times sine plus 1/2 the acceleration vector times t squared. So we can actually write down our kinematic equations from before for constant acceleration even in 3-dimensional space. The initial position could be in the x. The initial velocity can be in the y. The acceleration can be in the z. And this is still an expression that's going to give me the x, y, and z coordinates of the position at any given time that we chose to pick. But really what I wanted to highlight is this behavior right here, this behavior right here in particular. It turns out that if we have cases of constant acceleration, that each of these components is working independently of each other. There's nothing about what's going on in the x direction that impacts what's going on in the y direction or impacts what's going on in the z direction, except for time. Time is the only variable that shows up in each of these expressions. And this is going to be our link to something called projectile motion. So it's the easiest possible case of projectile motion where everybody starts is going to be looking at this particular case of two instances of constant acceleration. What we are going to have is a constant acceleration of 0 in a horizontal problem because there's no acceleration in that direction for free fall. Free fall says the acceleration of gravity is this way, but there is no vector component of acceleration this way in free fall motion. There's nothing else that's working on it. So what we have is constant acceleration that's 0 this way and a constant acceleration of g this way. Both of these components have constant acceleration. This acceleration is 0, but 0 is a constant. This acceleration is g, and g is a constant. So we're actually looking at this thing that I just laid out. A case of vectorially consistent constant acceleration. But because we have constant acceleration, it turns out that that vector expression of kinematic equations still holds. We can handle what's going on in the x direction and what's going on in the y direction independently of each other. The linkage between those two is the time. So what often happens in these types of equations is we come up with some system of two equations, and we commonly have two unknowns. If we have two unknowns and two independent equations, x and y in this particular case, we can solve that situation uniquely. If we have three things that we don't know, we need three equations to solve, so on and so forth. And so what commonly happens in projectile motions problems is we have things going on in two directions, up and down, right and left. And we have some information about what's going on in those problems. Maybe we're told how long it is in the air. So that tells us the time of what's going on. Well, if I know the time and a couple of other things, I can probably find what else is going on with the motion. That's pretty cool. Okay. Maybe we're told some parameters of the motion that's going to happen. So it has some motion that's evolving in the horizontal direction. It has some motion that's evolving in the vertical direction. Maybe the ball goes up, the ball goes down, and then it hits something. The ball is moving to the right consistently as it is going up and down. That's perfectly and totally fine too. But this is what's going on with classic projectile motion problems. We have two kinematic expressions in the x and the y, the horizontal and the vertical. Both of these accelerations are constant, so we can use kinematic equations to talk about it. So what we're going to do is look at those two different components independently and figure out how to find some things that aren't initially given to us in a problem. Okay, so casually, let's say we wanted to look a little bit about what this kind of motion looks like. So we can go into Mathematica. And here, what I coded in Mathematica is some ways to look at projectile motion. So maybe I wanted to start with some projectile at a height of 0 and an x position of 0. But, I want to fire it at some particular velocity, this projectile. I want to fire it at some particular angle with respect to the horizontal. So maybe 41 degrees, I don't know. And I see that as a function of time, its y position changes and its x position changes. Okay, so I can pick some particular amount of time. If I was to fire at a greater speed, or change the angle that was fired, we see that the motion is different. It goes to a higher height. It has a further range as a function of time. But I can see, it hits the ground again at about 4.7 seconds or so. That's how long it's in the air. Well, what if I was to fire a little bit differently? Now how long is it in the air? Much smaller time. As a much smaller distance. But, what is evolving? What is consistent in both the vertical and horizontal directions is the time. The time is the same for both. Time is evolving for each of them in exactly the same way. And it turns out because of that, there's really only certain trajectories that can arise. The ball is going to have to sit on a certain kind of parabola because we have parabolic motion. That's what kind of motion we have to have as this evolves. So we can start at initial heights that are big. We can start at initial heights of 0. We could actually go negative if we wanted to. We could fire at great velocities or small velocities. We could fire at big angles, small angles, or negative angles. We could be on different planets with different gravity, and as the system evolves, the projectile is going to fall on these parabolic paths. Okay? Now this is just sort of the setup for the problem to see how it works. Now this is one of the signature topics of the entire term. It's one of those things that I will joke in the future calling it nightmare fuel, because it is a big part of what you're probably going to remember about General Physics 1. This is a signature topic. Hint, hint, this is something that you're going to want to know how to do on exam 1, because I can guarantee that one of the large value partial credit questions is going to be a projectile motion problem. I guarantee it. I absolutely guarantee it. And I think it's so important that I've ended up going through and giving a lot of examples of problems that are ways to give you a good understanding of what projectile motion is all about. In this diver problem, what we have is some diver jumping off of a cliff trying to make it into the water pool below. But there is a step. The diver has to be going sufficiently fast or it's not going to clear the step. So this is one of those problems where I have something going on in the vertical direction, the diver is going to fall from the cliff. We have something going on in the horizontal direction, the diver has to make it sufficiently far in the x direction or they won't hit the water. So how long is the diver going to be in the air? And knowing how long the diver is going to be in the air, does that tell me how fast the diver needs to be moving so that they make the water? This is a classic projectile motion problem, and so I encourage you to look at this diver problem. The cannon is even more prototypical. I've got a cannon sitting on the ground. It's going to fire at some velocity, at some angle with respect to the horizontal. What's the range of this cannonball? How high in the air does the cannonball go? How long is the cannonball in the air? Perfectly and totally classic projectile motion problem. That's already worked out, so I encourage you to look at that video as well. In the monkey shoot problem, this is a classic problem of having two particles both undergoing projectile motion, free fall projectile motion, but we would like to come up with some scenario where these two things hit. So is there a way for me to fire one projectile at another projectile? Eventually both of them will be in free fall where one actually hits the other. How do I have to aim at something like a monkey that's going to be scared when he hears the gun go off? Where do I aim to hit him? Do I aim above? Do I aim below? Do I aim right at him? What does the math say? So this is a classic problem Don't sick PETA on me. Classic problem to look at. To look at not only how one particle, now one projectile is moving in this free fall motion in 2D, but how two particles can interact in that exact same way. We have other examples here where I've got a carnival game. I've got some dude that's going to be firing some projectile like a coin or whatever, and he has to get it into a cup. Well, how hard does he have to flip that coin? At what angle does he need to flip that coin in order to get it into the cup? Classic projectile motion problem. This last one here is one of these cases where, what if I'm told some other weird things? In each of these projectile motion problems that I've just described, you're essentially needing to find out what the time is to figure out what's going on in other parts of the problem. So if I figure out what the time is from, say, the horizontal problem, I can use that time in the vertical problem. Or I can find out in the vertical problem how long something is in the air, and I can use that information for what's going on in the horizontal problem. But what if you were given the time right off the bat? You know how long it was in the air. Now that's something that's not unknown anymore. That gives me the ability to find other things that I might not have known initially. So this is another case of a tweak. It's a slightly different look at a projectile motion problem that still applies in exactly the same way. I've got a lot of examples for projectile motion. Why? Because it's important, and I will guarantee you, expect you to know how to do this on exam 1. Now for us, I would just like to look at maybe a different problem. And we're going to pose it in maybe a slightly different way in order for us to look at it. I'm going to come up with a case where we have some particle, some projectile, and it's going to be fired at some cliff of height h, and we're going to fire from some distance r away. So I've got a cannon that's going to fire some projectile. And it's going to follow, some trajectory like so. So the particle's initial velocity, we don't know. But we do know the angle that the projectile makes as it leaves the cannon. So there's a couple of things that we know, a couple of things that we don't know. Now, I am going to work the problem in terms of these variables. But if we wanted to look at some math later, let's say that h is equal to 20 meters, r is equal to 60 meters, and theta is equal to 50 degrees. It's reasonable, it's fine, but we're going to do variables first, and then we're going to find some other things. So what is the point of the problem? I would like to find the velocity needed to hit the edge of the cliff, and B, time that the projectile is in the air. These are the two things that I would like to know. Now, when you approach a projectile motion problem, there are two things that you really should do all the time. You should write down what's going on kinematically in two directions. So in the x direction, I know that sum x final is equal to sum x initial plus v initial in the xt plus 1/2 a in the x t squared. And I know that y final is equal to y initial plus v initial in the y direction t plus 1/2 a in the y direction t squared. I don't have to do any thought. I'll figure out what I need from this later, but these are things that I know are true. So some things that I know in my problem, that after the sufficient amount of time, the time that I'm looking for in part B has passed, the projectile is going to be at an x position of r, and it's going to be at a y position of h. So I know at some special time that I'm going to be looking for later that x final is equal to r, x initial is equal to 0. The initial x component of velocity, I can use trigonometry to find that this is v cosine of theta t. How much acceleration do I have in the x direction? I have no acceleration in the x direction for this problem. Over here, in the time that I have found right here, the height is going to be h. My initial height was 0. My initial y component of velocity was v sine theta, but my acceleration is minus g. So now I have these two equations. R is equal to v cosine theta t, h is equal to v sine theta t minus 1/2 gt squared. And we know some stuff in the problem. So I know the angle. I know r. I know h. I know g. But in both of these problems, we have the two things that I don't know. I need to find the velocity, and I need to find the time. Here I've got velocity and time. If I knew one of them, I could find the other. Over here, velocity and time. If I knew one, I could find the other. This is a system of two equations found independently and two unknowns, vt, vt. And the way you solve systems of equations like this is to solve one of them for one of the variables that you would like to know. So I'm going to solve this for t. And from this expression, t is going to be equal to r over v cosine theta. Now, I don't know what v is, but I do know r and cosine theta. But what I do with this is take this thing and plug it into the other equation. This is what the time is. I don't know how to find out numerically what it is, but this is the time. So let's take this time and plug it in over here. It tells me that h is equal to v sine theta times r over v cosine theta minus 1/2 g r squared over v squared cosine squared theta. Now this can be simplified a bit more. Sine theta over cosine theta is tangent theta. V over v is 1. So this is r tangent to theta minus g r squared over 2 v squared cosine squared theta. That's what h is. Now I know h, I know r, I know theta, I know g, I know r, I know theta. The only thing that I don't know in this expression is v. I can solve this thing algebraically for v. So I see that g r squared over 2 v squared cosine squared theta is going to be equal to r tangent of theta minus h. Okay, well, I'll just swap these two things out. V squared is going to be equal to g r squared over 2 r tangent of theta minus h cosine squared theta. Or v is equal to square root of this whole thing. And I'll keep the r squared under the square root. And we know all of those things. I know g, I know r, I know 2, I know theta, I know h. So I can solve this. Let's pull out our calculator. Let's look at the bottom here first. So we've got 50 here. 50 times cosine theta. Actually, let's do the inside of the bracket there first. Why not? So 50 tangent times r, which is 60, minus h, which is 20. That's the parentheses. So I take this whole thing times 2 times the cosine of 50 squared is equal to this. Put that in the denominator, times 9.8 times 60 squared. Take the square root, and I get 28.8 meters per second. That is the speed required at cannon launch to get to that particular point. Now, if I know this velocity, I can take this velocity and plug it back in over here. Now I would know r, v, and theta. That gives me a unique value for time. So we still have our calculator up here. We have the velocity. So let's take this velocity and multiply by cosine of 50. So times cosine of 50 is equal to this. Put that in the denominator and multiply by r. So it is in the air for 3.24 seconds. Yeah, so we can do a problem like this. This is the time. This is the velocity. These are the things that we were asked for. So we can actually do this. Now, do we trust this? Let's take a look in Mathematica to see if it actually works the way that we anticipate it to. So we come back here to Mathematica, and we've got some way of looking at trajectories from known systems and how they go. So in our problem, we were firing from the ground. We were firing at an angle of 50 degrees. Firing at an angle of 50 degrees. G on the Earth is 9.8 meters per second squared. That's what we were using. And we wanted to find out the velocity needed to get to a certain point and the time needed to get to a certain point. And we found a time of 3.24 seconds. I have, 3.24. Great. And we said that the velocity that was needed was 28.8. And lo and behold, I look at this. We start at time t equals 0. The projectile rolls along until at 3.24, sorry. We are right here. Its x position is 60, its y position is 20. That's what we anticipated. That's what we anticipated. So yeah, it works the way that it's supposed to. Now, one last thing that I wanted to point out before we left is there's a lot of stuff that is parabolic about this system. So we see here that we've essentially set up the problem so that there's a potential for parabolic behavior in time in either of these directions that had constant acceleration. We happen to choose ax equal to 0 for traditional cases, but there could be some where it's not. It's just some other constant, that's totally fine. But we get this parabolic quadratic behavior in time. And we see that that is going to be the case from Mathematica, because for a lot of projectile motion problems, let's say we only knew we were trying to find some time to where the projectile gets to a height of 20. Well, there's lots of trajectories here where it gets to a height of 20 one time, then it gets to a height of 20 again. We start at a height of 0. We end at a height of 0. There are often 2 times where something happens. But it turns out that this is not the only way that this behavior is quadratic and or parabolic. Another way that we see this parabolic behavior is set up in a slightly different way. Now we start the problem the same way we did before. X final is equal to x initial plus v initial in the xt plus 1/2 a in the x t squared. Y final is equal to y initial plus v initial in the y, t, plus 1/2 a in the y, t squared. And typically what we're looking at is some r is equal to 0 plus v cosine of theta t plus 0, h is equal to 0 plus v sine theta t minus 1/2 g t squared. This is the typical kind of setup. And over here, just like before, we see that t is r over v cosine theta. And because of this, plugging this time in over here, h is equal to v sine theta minus 1/2 g r squared v squared cosine squared theta. So this is r tangent of theta minus g r squared over 2v squared cosine squared theta is h. Now this looks pretty complicated. Maybe if we knew v here, we would know everything except for angle theta. But solving for this algebraically is a real mess because I have tangent of theta here and I have cosine of theta here. If I wasn't initially given the angle, this is potentially a hard problem. And what I'd like to illustrate is remembering that sine squared theta plus cosine squared theta equals 1. What if I divide both sides by cosine squared theta? Sine squared theta over cosine squared theta is tangent squared theta. Cosine squared theta over cosine squared theta is 1. So this is 1 over cosine squared theta, and we have one of those things. Another way to write this is r tangent theta minus g r squared over 2v squared 1 plus tangent squared theta. And what we see from this expression is even if we knew velocity, r, g, h, all of those things, and we needed to find out what theta was, we are now quadratic, parabolic, in tangent of theta. Now I could solve this algebraically. So there's two angles that will give a particular result. And usually what you might think of in terms of this kind of expression where you're given some velocity, maybe it's a high velocity or whatever, it turns out that oftentimes what happens is maybe I'm firing at this cliff face and I can hit the edge of the cliff with the projectile going up, or I could hit the edge of the cliff with the projectile coming back down. But I would fire at two different angles to do those two different things. My pop gun only has a particular size, but I could fire it in whatever direction I want. And to hit something, I might want to hit it with the projectile coming from above or the projectile coming from below. That's these two angles. So we have this quadratic behavior in angle, just like we have the quadratic behavior in time in some scenarios. And just before I end this particular lecture, I wanted to point out something else from the problem when we first started it here. This is the same page that I had before. We had the velocity, 28.8 meters per second, the time, 3.24 seconds. I want to look at this thing in particular, because it turns out that if r tangent of theta is not bigger than h, this isn't real. This becomes an imaginary number, and there is no velocity, no real velocity, where I could hit the edge. So how do I ensure that r tangent theta is bigger than h? Well, first of all, what is r tangent theta? The tangent of theta is h over r. So this is h. This is basically for some kind of a extreme case of theta. This is the theta that's going to lead to problematic behavior, potentially problematic behavior. But if my theta is not at least h over r, I can't solve the problem. If theta, the tangent of theta, is h over r, we get a 0 in the denominator, which is a problematic, but at least it's a real problem and not an imaginary problem. But as long as tangent of theta has to be bigger than h over r, it has to be bigger than h over r, this is the only way that we can get real solutions. So if I wanted to, I could actually do some quick looking and find out, well, making sure that the numbers are what the numbers are, is this going to work? And it turns out that, yeah, the angle that we were firing, so 20 over 60, let's pull up a calculator here. So tangent of theta has to be bigger than h. So here are 50, the tangent of 50 is 1.19, but h over r is 20 divided by 60, 20 divided by 60, which is a third. Tangent of theta is bigger than h over r. That's why we found real numbers. That's why we found a real number. Okay. Now, this is just to give you a little bit of flavor on motion in more than one direction. We have one more lecture component, part D, that's going to look at circular motion and relative motion. It's also going to be relatively short. And while this particular lecture is short, I would strongly, strongly, strongly encourage you to go through and look at these examples that I've done for you. This is an important part of this lecture, is going to these things and learning how to do the diver problem, learning how to do the cannon problem, learning how to do the monkey shoot problem, learning how to do the carnival game, learning how to do a problem when you're given some things that are maybe a little unexpected or unusual. How do you really approach these? But all these projectile motion problems are done in exactly the same way. And so hopefully this is relatively straightforward and you get a lot of good out of it. As always, if there's questions and concerns, reach out on the discussion board or try to get a video chat with me. Good luck.